Hey guys, what's going on? Welcome back to the channel. We are talking about parametric differentiation today, and we have talked about explicit differentiations, implicit differentiation, and last thing that we learn is the parametric differentiation. Those are all the three that we know so far in mathematics. So let's get started with the first one we call the explicit differentiations. Explicit differentiations. This first type that we always learn this. Second type, we learn implicit differentiations. And lastly, the one we learn today, which is very easy, I'll show you by an example and you see straight away. Parametric differentiations. So what's the difference between them? Explicit differentiations means that y can be presented in terms of x, which is a function y equals fx, and then you can differentiate normally, like y dash is dy over dx. Straight up, you have the answer by using tools like I'm going to write out tools down here so people can see what kind of tool do you use for each of them. Just make sure I highlight um, the types of differentiation first. So this one is explicit, this one is implicit, and this is parametric differentiations. Very much the same as well. So I'll swap about the form first. So the form for explicit differentiation is in fact just y equals fx. So clear as day. There's no hidden meaning behind this. Implicit differentiations, we have some sort of connection between x and y linking by equations. So x and y are linked by an equation, but it is not easy to make y the subject. And therefore, that's why we need implicit differentiation, because we can't explicitly write y in terms of x. All right, so that's the deep meaning behind doing this. Okay, and lastly, we talk about parametric differentiations. So this is a new thing we learned today. It's not too hard. So x and y cannot be linked together. X and y can be linked in some way. So x and y are linked by the third variable. Here we go. This is where things get interesting. By the third variable. Um, because it is not easy to link x and y in one equation. So this is the next level, right? Because it is not easy. It's not always easy to establish a direct relationship between x and y. Okay, so again, explicit differentiations, straight away, y is something in terms of x, very direct, very clear. Implicit differentiation, somewhat, you can still have an equation to represent their relationship. Parametric equations, it means x and y are linked by a third variable, and it's quite hard to find a direct relationship between them. And that's why we need to borrow the third one. So in theory, it will look like x will be something like x will be a function of a third variable, which is t, and y is going to be gt. So this one means t being the third variable. So x is in terms of t, and y is also in terms of t. So x and y are linked together by t. So So when t behaves, x and y is gonna behave as well. It's gonna so t is the variable and x change according to t and y also change according to t. Somehow they still link together via t, but yeah, but there's no obvious direct relationship between them. Let's look at an example and you will see for yourself what's happening here. Let's say example here, phi dy over dx, where x is going to be 2t and y is going to be t cubed plus 6t squared. This kind of thing, right? Fairly simple. What you have to do is because x is in terms of t and y is also in terms of t, so straight away we can phi dx over dt, which is 2, and also dy over dt is going to be 3t squared plus 12t. There you go. And because we are finding dy over dx, so we can do this trick right here, dy over dx. It's going to be dy over dt times dt over dx. You see that we borrowed the dt down here and dx and also dt up here. It's going to split the fractions. In fact, if you imagine, this technique is more like saying, I'm going to write down an example down here so you will understand better. So if I say 3/4, it's going to be the same as if I slide down, if I'm going to slide in a number, I'm going to slide in a number down here. So 3/8 times 8/4. See that? Same answer, right? That's a very nifty trick. Okay, so let's move on. So I know dy over dt. I know it's going to be 3t squared plus 12t. And then dt over the x here, I have the x over dt, which is the opposite, the upside down one. So I have the x over dt up here, but now this one is dt over dx, which is the upside down of the x over dt. So therefore I flip this one upside down. So I flip this one upside down. Oh, kind of makes sense, right? So if I flip one upside down, I have a fractions over 2, and this is the answer. Of course, you would expect the y over the x also in terms of t, because we have y is in terms of t, x is in terms of t. Therefore, dy over the x is also in terms of t. Just because it's kind of hard to find a direct relationship between x and y. Therefore, we borrow the third variable to be in terms of t, and this is what we call parametric differentiations from the one on top, from parametric equations. Okay, let's go over a Cambridge example, a Cambridge question here. So this is the Cambridge exam from 2006, I believe. So if I have x, put a line through here, 2 theta plus sine 2 theta, and y is 1. So as you can see from this example here, theta is our third variable. X and y is in terms of theta minus cos 2 theta. You can imagine, theta being the third wheel. X and y, there's no clear relationship between x and y, and theta just jump in between. That's very sad. So theta is like a third wheel, if you might. So if the question is say show that. dy over dx equals tan theta. Now we precisely want the same technique as well. We can go ahead and find the solutions. We will go ahead and find dx over d theta, because I'm trying to differentiate x with respect to theta. So I'm gonna do 2 here. So here I'm gonna use chain rule. So sine will become cos 2 theta first, and then times by 2 theta dash. Of course, with respect to theta, right? So 2 plus, or 2 theta dash will become 2. So put 2 in front for the sake of simplicity. Okay, so that's just done with dx over d theta. Now I'm going to find dy over d theta. It's going to be, for dy over d theta, one will become 0 when I differentiate. The minus belongs to cos, so I have minus sine, because cos becomes minus sine 2 theta, and then I times 2 theta dash. There you go. So if I have this one, sine 2 theta times 2, here we go. So if I'm finding dy over dx, I just need to use the nifty trick that I talked about above. It's going to be dy. So this is a big finisher, dy over dx. It's going to be dy over d theta. So you literally just slide in the third variable, which is theta, times d theta over dx. So dy over d theta itself is 2 sine 2 theta, and you flip the dx over d theta upside down. So flip that dy upside down, I got 2 plus 2 cos 2 theta. Now it's a job to simplify this guy down to tan theta, right? Somehow, you can see clearly that we got to use a double angle formula somehow here. So the first thing I'll do is I'm going to divide the top and the bottom by 2 first. So sine 2 theta over 1 plus cos 2 theta. Now if I read the formula in the formula sheet, sine 2 theta is going to be 2 sine theta cos theta, and then I will use again the double angle formula for cos 2 theta, right? So cos 2 theta in the formula is actually 2, so 1 plus cos 2 theta in the formula is going to be 2 cos square theta minus 1. So if I continue to do this, to simplify, I have 2 sine theta cos theta divided by 2 cos square theta. Very nice. Now I can see I can cancel out a 2. I can cancel out a cos as well, which is very handy. I can divide by cos, the top and the bottom, by cos theta. So cos theta is gone. Boom. So I'm left with sine theta over cos theta, which is exactly the same what we want. It's actually tan theta. And well, guys, it's game over here. All right, stay safe. Peace.